1.4 is going to continue our conversation about limits and continuity, but we're going to bring in functions that so far have been missing from our conversation. So we want to look at some trig functions, some exponential functions, and some log functions. Now, we have to start with a theorem we're going to use specifically to prove one of our trig limits. So we're going to start with this, what's called the squeeze theorem, or sometimes called the sandwich theorem. And so essentially it says, suppose we have a function g of x, and my goal is probably to find a limit involving that g of x function. But I've run into some obstacles, and I can't maybe just evaluate it so directly. But if I can get it squeezed in between, or sandwiched in between, two other functions. So if I can get g of x greater than or equal to some f of x and less than or equal to some h of x, if that inequality holds, then it should also be true that any kind of limit of that inequality would hold also. So what we're really kind of saying here is, if this inequality is true, then certainly the limit as x approaches c of that inequality should also be true. So the limit as x approaches c of f of x should be less than or equal to the limit as x approaches c of g of x, should be less than or equal to the limit as x approaches c of h of x. All right, well then, if I know that the limit as x approaches c of f of x, if I know that this limit is equal to L, and if I also know that the limit as x approaches c of h of x is equal to L, now I have some quantity that I'm in search of, the limit as x approaches c of g of x. I have that is both greater than or equal to L and less than or equal to L. Well, in order for that to be true, that of course implies that this limit has to equal L. So let's just look at a couple of examples here. Let's come back to number one. Let's actually start with maybe a shorter example for number two. So let's use the squeeze theorem, or again, sometimes called the sandwich theorem. So let's use the squeeze theorem to find the limit as x approaches 1 of g of x given, and so this might be the type of thing you could see in your homework as an example, that negative x to the fourth plus 3x plus 2 is less than or equal to g of x is less than or equal to 3x squared minus 4x plus 5. Okay, so let's take a look at that. All right, so given this, we already have, in some ways, the hard work done on this one. We already have g of x sandwiched in between or squeezed in between these other two functions. So what we know then is our limit as x approaches 1 of this inequality is going to hold. So essentially, I'm going to be taking the limit as x approaches 1 of my negative x to the fourth plus 3x plus 2, and that's less than or equal to my limit as x approaches 1 of g of x is going to be less than or equal to the limit as x approaches 1 of the 3x squared minus 4x plus 5. All right, now let's actually evaluate these limits. So if I simply evaluate, these are nice polynomials, direct substitution, so this is going to be negative 1 plus 3 plus 2, so that's going to be 4, is less than or equal to, and this is the limit that I'm being asked to find, and that's going to be less than or equal to 3 minus 4 plus 5. So again, we're just evaluating that limit at x equals 1. So if this quantity I'm searching for is both greater than or equal to and less than or equal to 4, then therefore that implies that this limit has to equal 4. So that's the idea behind the squeeze theorem. Let's also now go back up and take a look at this number 1. And so we have a graph, and we can kind of visually see this squeeze theorem working here. We have this function g of x, which is x squared times sine of 1 over x, and we're interested in finding this limit. And so if we were to think about, looking at doing direct substitution on that, you can see why this would be a problem, because if g of x is sine of 1 over x, if you were trying to sub in 0, then you'd have 1 divided by 0, and we couldn't evaluate that. So here's what we have. We have kind of this visual where we can see, yeah, our function is sandwiched or squeezed in between the x squared and the minus x squared. So we kind of have the visual of that. So we have a notion of what my f of x and my g of x are going to be here. I'm sorry, my f of x and my h of x. So the two functions. Now, it should be said that this property, this inequality that we're establishing, doesn't need to be true everywhere. It just needs to be true in some interval around the limit that we're trying to find. So that should be kind of stated as well. All right, so let's go ahead and see if we can establish this inequality by hand, essentially. So here's something that will come up frequently, actually, for us, is that when you think about the function sine and cosine, I want you to always be thinking about when you graph either, sine, or if you were to graph cosine, cosine of x, or if you were to graph sine of 2x, or cosine of 3/2 x minus 1, kind of anything in there. Cosine of any theta, sine of any theta. Sine and cosine, they are always their output values. Think about the unit circle. Think about the graphs of sine and cosine for any input x value. The outputs always range in between -1 and 1. Excuse me. All right, so with that said, what I want us to observe here is that what we have is we have a sine function, and it's sine of something, sine of 1 over x. So sine of any theta is always going to be bound between -1 and 1, and that's really the key. Now, what we're going to do is we're going to say, okay, if that's true, then I should be able to multiply this inequality through by x squared. And so that's what we're going to do here on our next step. So remember, if you were to multiply through by a negative, that would reverse your inequalities. X squared is obviously positive, so that's just something to be mindful of in general. But here that means I'm multiplying every portion of this compound inequality. It's really two inequality statements put together. So I'm multiplying everything through by x squared. And now that I have my inequality established here, that's the function I wanted, right? This is my g of x. I have g of x sandwiched in between two other functions. So now what we're going to do is now we're going to say, okay, so now we can, take the limit. So now we're going to take our limit as x approaches 0 of that inequality. So now we know that the limit as x approaches 0 of -x squared is going to be less than or equal to the limit as x goes to 0 of this x squared sine of 1 over x is less than or equal to our limit as x goes to 0 of x squared. Now we can actually evaluate these limits. So now when I evaluate these limits, this is simply negative 0 squared, that's going to be 0. On the far right, that's just 0 squared, that is going to be 0. So now I have the limit that I'm interested in. The limit as x approaches 0 of x squared sine of 1 over x. I have that sandwiched in between, squeezed in between 0 and 0. So then by the squeeze theorem, if this limit is both greater than or equal to 0 and at the same time less than or equal to 0, then that means that this limit has to equal 0. All right, so that's your introduction to the squeeze theorem. When we come back, we are going to look at using that squeeze theorem to prove an important trig limit.